Okay, so this whole module is on trees and graphs. We've done an awful lot of work with trees, but you're probably wondering, when are we going to get to the graphs? And well, this is it. We're now going to make a tour through graphs, and I think you'll understand why this is so much more abbreviated than trees. Okay, so there's a couple of ways of doing this, and the way that I like to do it is to introduce graphs as kind of a generalization of trees. Some other books do it differently. They might, for example, introduce graphs first and then say that a tree is a special kind of graph. Either way works, okay? But I actually like this idea that that is a generalization. So what we have is, just as with trees, we have a bunch of nodes. So here's one node, another node, another node, another node, another node, another node, and so on, okay? Sometimes they're called vertices, the exact same meaning. Nodes, vertices, same things, okay? And then we're going to have edges that go from one node to another, from two, so I'll draw arrows, okay? So that's kind of what it looks like, okay? There's no restrictions on the edges, okay? From one node to another, you can only have one edge. Otherwise, you're dealing with a multi-graph. That's allowed to have more than one edge between nodes. But generally speaking, this is it. We have nodes, and then we might have an edge from one node to another node, right? That is it. So here's an example of a graph, and as you can see, there's not much to see, right? It's just a bunch of nodes and then arrows or edges connecting them. All right. Now, here are some other examples just to give you a flavor for everything. Okay. So right here, G1. You see that there's lots of, well, this node here has 3 children, right? This one has 4. There's nothing really regular, right? Look at this one here. If I look at this, that just looks like that, right? And then there's all the other stuff, but those are actually like two things that are overlapping. There's nothing in common between these two sections of the graph, right? Right? It looks like that. This is like part 1 and that's part 2. They're separate. Interesting, right? I mean, there's just so much variety. There's a lot of things that you can do, okay? But one of the things that I really want to drive is that there is no root, okay? Right? There's not a single node that I can point to and said, I start here and then I go to the other ones. There's no preferred node, okay, like there is for trees. So that's one big difference, okay? And that has kind of a major consequence, okay? Here are some of those consequences. So you can't just give a root node, okay? And worse than that, they can be disconnected. Remember, we saw that graph that actually had 2 parts. So what we need to do is we need to have an explicit set of vertices, okay? So to be able to talk about a graph, I need to tell you what the vertices are. I can't just kind of let you find them. I give you the root and then you just follow the edges and you'll get everywhere. That doesn't work anymore, okay? So that's one problem, okay? And then I need to have the vertices. Now, what's a vertex? A vertex is just kind of I mean, we draw it as an arrow, but really what it has is a from vertex, a from node, and a to node, right? From vertex. So the edges, and I'm sorry, I said vertices. The edges are composed of a from vertex and a to vertex, or a from node and a to node. So what are they? They're just pairs of nodes, right? That's really what the edges are. So I can now kind of say all this mathematically, right? So what exactly is a graph? A graph looks like this. It looks like 2 things. V, which is just a set of vertices, and then E, which is a set of edges, right? And an edge is nothing more than an ordered pair of vertices. Okay, so look at edge, and since each edge is an ordered pair of vertices, the set of edges is just a set of ordered pairs of vertices. So the edges are a subset of V cross V, okay? because that's what the order pair of vertices look like. Okay, so now we have kind of a formal mathematical definition of a graph. A graph is a set of vertices and a subset of the vertices squared. Okay, interesting. I wonder if that reminds us of anything. Okay, so just to make sure that we're on the same page with that, let's consider this graph and let's try to write it as VNE. Right, so here's the set of vertices. So we have 2, 3, 5, 2, 3, 5, 7. Notice there's no 6. Okay, 8, 9, 10, 11. Okay, so yeah, those are all of the vertices. You have to be careful. It's very easy to miss one. Okay, now how about the edges? Okay, the way that I'm going to show them is kind of in alphabetical order or lexicographic order. So I'm going to start with 2. Any outgoing edge? None. So we're done with that. So the next one is 3. Outgoing edges? Yes. 8 and 10. So we have 3, 8, 3, 10. 4, there is no 4. 5, yes. 5 has an edge to 11. There it is. Okay. 6, there is no 6. 7 has 2 edges to 8 and to 11. So 7, 8, 7, 11. 8 has 1 outgoing edge to 9. 10 has no outgoing edges. And finally, 11 has 3 to 2 to 9 and to 10. So that's how we represent graphs. Okay, that's it. It's just a set of vertices and a set of edges. It doesn't look as pretty as the pictures, but maybe we can deal with it mathematically. Okay. Now, why do we do the graphs? Okay. Well, actually, graphs are tremendously useful. So here's a graph that, for example, Google Maps might use to route you. So let's say that you want to go from Cheyenne to Thermopolis, then you would take a path down this tree. Actually, I'm sorry, down this graph that will get you to Thermopolis, right? That's how this works. We have other kind of graphs. Here is a dependency graph. This is a graph that tells you what courses you have to take before what other courses. So here we are. Discrete math, right? And according to this, you have to take discrete math before algorithms, before functional programming, right? And after 1030. Okay, so that's the dependency graph. The reason that it needs to be a graph is that, for example, 3020 has several parents. It needs 2300, but it also needs 2150, right? And you might find conversely that, well, something like 3020 itself actually has lots and lots of children, so to speak. So it isn't just as simple as one parent, many children. It's many parents, many children. That's what makes it a graph as opposed to a tree. Okay. Okay. Here is the rest of that dependency graph. 3020 is the bottleneck in our program. You can see that very clearly here. So yeah, that's one of the nice things about graphs. Okay, so let's go back to the mathematical definition. And like I said, that should have reminded you of something. Because a graph is a set of vertices and then a subset of the vertices cross the vertices. And what that really might remind you of is a relation. Okay, because a relation R between two sets, S and T, is a subset of S cross T. V, or rather E, the edges, is a subset of V cross V. So a graph is really just a relation between the set of vertices and itself. Okay, just between you and me, you can actually have graphs where the set of vertices are split into two parts, S and T, and those graphs are called bipartite graphs. So even the classic relations between two different sets actually end up being graphs. So yeah, relations on graphs are the exact same thing. The only difference, if you want to call it that, is that when we talk about graphs, we usually have a pictorial representation in mind. Okay, when we talk about relations, we don't. That's it. That's the only difference, right? One of them lends itself to graphs because we think of it that way, and the other one doesn't. Go figure. Okay, so that's the difference between relations and graphs. That's why when I'm talking about trees and graphs, I don't have to spend a lot of time on graphs because we spent a lot of time on relations. Okay, everything you learned about relation applies to graphs. So I'm just going to assume that we know all that, right? So what can we talk about a graph? We can say that a graph is reflexive. That means that there is a vertex from each node to itself, right? So whenever you have a node, there is always a loop that goes into that node. Okay, That would be a reflexive graph. Okay. Now, how about symmetric? Symmetric means that if I can get from A to B, right, that can also get from B to A. That's it. That's what a symmetric graph looks like. By the way, in graph terminology, we usually call those, quote, undirected. Okay. And then what about transitive? If I can get from A to B, and I can get from B to C, then I can also get from A to C in one step. So this edge has to exist. And that's it, right? So we can talk about symmetric graphs, reflexive graphs, transitive graphs, and it's the same that it was for relations, right? What about ideas such as G1 union G2? Yes, absolutely. Just take the union of the graphs by taking the union of the edges, union of the vertices, right? How about the cross product? No problems. We'll take the union of the vertices so we don't lose anything, right? And then if I have A, B, and C, right? So this is an edge in R1 or G1, and this is an edge in R2 or G2, right? Then this is an edge in R1 cross R2, or if you will, G1 cross G2, okay? So that's what it means to take the cross product. Easy, right? What about G1 to the fourth? Just take it 4 times, and you'll get G1 to the fourth. How about G1 inverse? Swap the direction of all the arrows. That's it. Okay. So yeah, all of those properties apply to graphs. Can I get the transitive closure of a graph? Absolutely. It is the smallest graph that is a superset of the original graph and is transitive. I'm sorry, and is reflexive. So yes, I can talk about all those properties. Very, very, very nice. That's the stuff that we already know. Okay. So instead of talking about those things, I'm going to talk a little bit about how to represent graphs in code. Okay, so here's a graph, and how do I want to represent it? Okay, now for trees, the way that we represent it is simply by having a pointer to the left and the right subtree. Okay, you might have a list of subtrees in the case that it's not a binary tree. Okay, easy. That was a representation. For graphs, we can't do that. Okay, so instead, what we have to do is kind of keep track of everything. So we'll keep the list of neighboring vertices for each vertex. So let's start here. From A, I can get to B. So that is represented right there. Okay, the list of children of A, if you will, although children is kind of a weird notion because it can go in both directions, right? But the list of the children or successors of A is B. How about B? I have 2 different outgoing arcs. So B actually can get to C and D. Okay, from C I can get to E. That's this. From D I can get to C. That's that one. And finally from E I can get to D. That's that edge, right? So for each node, we simply keep a list of all of the nodes that are reachable from it by 1 step. Okay. This code, by the way, here is just Python code. That's not important, but what is important is that I wanted you to know that I actually have the code for each one of these graphs. So it really is represented that way. Okay. All right, so let's look at some other ways of representing it. Different ways to use a matrix, and this is called an adjacency matrix. Adjacency matrix. The previous explanation was called an adjacency list. Okay, adjacency list. So anyway, so let's take this this guy here. So that is in the 3rd row, 2nd column. And then what he has is, this is equal to 0 if there is no edge from 3 to 2, right? And these are just node indexes, right? Is a 1 if there is an edge. That's it, right? So for example, there's an edge from A to B. This is A, B, C, D, E, right? Those are the from, and then the columns A, B, C, D, E, all right? So from A, I can get to B, and notice that 1, that is because of this arrow, that is a 1. Notice that all of the other entries are 0 because there's only one way to get out of A, right? Now let's look at B. You can get to C and D. So from B, you can get to C and D. There you go. And everything else is 0. And so on, right? That's how you build this adjacency matrix. So we actually have 2 established, accepted, traditional ways of representing matrices in code. Adjacency lists and matrices. Okay. In fact, between you and me, it's kind of the same way, because the adjacency list is actually also could be considered as like the sparse matrix representation of a matrix. That's something that you'll see in like a numerical linear algebra class. Or so if you haven't taken that, you don't plan to take it, don't worry about it, right? There's just two different representations: adjacency list and adjacency matrices. Okay, so here's an adjacency matrix. It's got a bunch of zeros and ones. Maybe I mean Booleans, maybe I mean numbers, right? So what's the difference, really? Okay, so let's say they're Booleans, right? So if they're Booleans, I need to be able to add them and get a Boolean, multiply them and get a Boolean. So I'm going to define plus and minus in this way. Okay, and there's the pen. Okay, so that's the way I'm defining plus and minus. If you look at that very carefully, that looks an awful lot like or, right? And this one, well, that looks an awful lot like and. So yeah, or means plus, and means times. I think we've seen that before, right? That's kind of a common scenario. Okay, now what can I do if I define it that way? Okay, well, I want to remind you about matrix multiplication. And with matrix multiplication, what we do is we multiply a matrix that is an m by n matrix, and we multiply it by n by p matrix, and the result is an m by p. Okay, and what we do is we go down a row here, and we go down a column there, and we just take products of corresponding terms, and then we add up all the products. So and that becomes this entry. Okay, so this is the first row times the first column. And this one would be second row times second column. And this one, for example, would be third row times second column. Okay? And if I look at it, right, that is 1 times 1 plus 0 times 0 plus 0 times 1 plus 1 times 1. And if you remember our definitions, 1 times 1 is 1, 0 times 0 is 0, 0 times 1 is 0, 1 times 1 is 1, and then 1 plus 0 is 1, plus 0 is 1, plus 1 is 1. So that is 1. And that is, in fact, the entry here, right? And so we just do that for all of those, okay? Now, so that's why we're adding and multiplying, just so that we can do matrix multiplication, okay? So suppose that we can. Now, what does that actually mean to graphs, okay? Well, here's something that it means. Suppose that I have a graph of a reflexive matrix, okay? That means that I can get from each node to itself. Well, you know what? That means that there has to be a 1 in each of the diagonal entries, right? Because I have a matrix, okay? And along this diagonal, I get any given entry might be row C, or rather node C to node C. That has to be a 1 because it's reflexive. All of these are going to be 1s. Okay, so yeah, I can actually recognize a reflexive graph by its matrix. Right. The same goes for symmetric, because if I try to do a symmetric matrix, then what I can do is flip it. Okay, and if I flip it, then that's like flipping all the direction of the arrows, right? So what happens is, since I can flip this and that, then what we actually have is the same matrix. And matrices that have that property are actually also called symmetric, right? So if I have a symmetric graph, I end up with a symmetric matrix, okay? And like I said, in graph terminology, the more common term for those is actually undirected graphs. Okay. What about unions? Well, that's just the sum of the matrices, okay? Now, I'm assuming that I don't get any more vertices, okay? If we do get any more vertices, just make the matrices a little bit bigger, okay? But then we'll just add them, and that actually is the union of the two matrices, because the union will have a 1 if there is an edge from A to B in either matrix, right? Because 0 plus 0 is 0, and everything else is 1. Perfect. What about A cross B, right? So what A cross B is supposed to mean is I start with a node in A, I follow it, and I end up with a node in B, which I then follow to get to C, right? So I have an edge in matrix A, and then I have an edge in matrix or graph B, and I just follow those two edges. Okay, that's actually the product, okay? Because when I take the product of two matrices, I get a 1 if, in fact, any one of those two kind of pairwise terms is 1. And when is one of those two pairwise terms 1? When I can go from A to B to C. Okay? So that's just absolutely beautiful. Okay? Because what it really means is this. I got two nodes, right? A and C. And the question is this the case? This is B1. This is B2. Is this the case? This is B3. Is this the case? And I do that for all nodes that are kind of in common. Okay, so basically the product is a 1 if there's some way to get from A to C in 2 steps. Okay, that's if they're Boolean. If I had actually left them as just numbers, then what it would have is the number of ways to get from A to C, right? Which is actually kind of nice. That might be useful to keep. So both of those work. Okay, so what about the reflexive closure? Well, for the reflexive closure, I start with A and I union the list of all A, B, B, C, C. That is the 1 along the main diagonal. So really what I need to do is just take A and add to that a 1s in the main diagonal. That's the identity matrix, okay? So this is actually the reflexive closure. What about the symmetric closure? I take A, I take the transpose of A, right? And then I union those, right? So what exactly is the transpose of A? That has a 1 from A to B if I can actually go from B to A in A, right? So yeah, that flips it. Take the union, which means add for matrices, is exactly the same as what we did with relations, okay? What about the transitive, the transitive closure? Well, the transitive closure means I have A, and then I add everything that I can get to in 2 steps, and then everything that I can get to in 3 steps, everything that I can get to in 4 steps, and so on. That's actually A plus A squared plus A cubed plus A to the 4th, and so on. Again, to really understand that, what you have to realize is that A squared is just all the nodes that I can reach in 2 steps, right? A cubed then will be all the nodes that I can reach in 3 steps, and so on. And I'm just taking the ors of those, which means add the matrices. Okay. Reflexive transitive closure. Well, that's just the transitive plus the reflexive, right? So easy enough to do. We got the whole thing. Okay. All right. Just one last thing that I want to leave you with. See that term I plus A squared plus A cubed plus ... That is kind of similar to this expression. 1 plus x squared plus x cubed, and so on, right? Here, what I have are real numbers. Here, what I have are matrices. Okay, that's the difference. Okay, but one thing that is true is that for real numbers, this sum is actually equal to this, right? How come? It's just a like a geometric series. Okay, so yeah, we can actually build that geometric series. Very, very nice. Okay, so I'm not going to prove that. Okay, we're just not going to prove that. However, I will tell you that there's a very similar result for matrices, and that is that I plus A squared plus A cubed is actually equal to 1 over I minus A, except there's not 1 over because there's no there's no division of matrices. There is instead matrix inverse, which is similar role. So it's actually I minus A inverse, and that is the transitive reflexive or the reflexive transitive closure of the matrix A. I think that's just absolutely amazing.